Hi everybody and welcome to session 16 of Field 2002, Logic, How to Defeat Your Foes with Reasoning. In the previous session I introduced you to a new language, general predicate logic. General predicate logic expands on monadic predicate logic by taking those predicates that we use to represent properties and dialing up their complexity by making them capable of representing relations between 2, 3, 4, or indeed an infinite number of things if we want to. So if we're talking about a basic property that we're interested in monadic predicate logic, we'll use a predicate like bx that just says that this one thing x has the property. But when we're dealing with relations, what we now have are things like bxy, which enable us to say that x stands in some relation to y, maybe the bigger than relation, where we'd be saying that x is bigger than y. What we did, in particular in the last session, was just really focus on the syntactic structure of what it is that we're doing when we introduce these new items into the language. We also introduced a new metaphor for thinking about quantifiers, because every time we're dealing with these complex predicates, where we've got 2 or 3 places following them, we're running the risk of having to deal with multiple quantifiers at once. And whenever we're dealing with multiple quantifiers, we need some way to think through the situation because it can get quite complicated quite quickly. What we're going to do in this session is expand our understanding of the syntax in 2 distinct ways. The first way is we're going to think about the relationship between the ordering of the quantifiers inside a complex sentence when you've got quantifiers appearing in it, and the meaning of that sentence. There are some cases where the ordering of the quantifiers actually makes a difference, and there are other cases where the ordering of the quantifiers doesn't make a difference. What I'll be doing as I go along is drawing pictures of each of these different ways of thinking about the quantifiers in order to highlight the kinds of implications that the ordering has for the meaning of quantified statements. The last thing we're going to do is introduce the concept of identity, which is another moving part of the language. In some sense, it's already there in germ, inside general predicate logic, but we're going to draw it out explicitly, give it a syntactic account, and then include it in our language and use it to do some translation. Alright, so first thing we're going to do though is look at these nested quantifiers. So by a nested quantifier, I mean any statement that has multiple quantifiers in it. So if you've got something like this, for all x, for all y, for all z, if axy, then by and cz, then what you've got is a statement with 3 distinct nested quantifiers in it. X, y, and z. And those are connecting to different variables. The x connects to the x variable, the y connects to the y variable, and the z connects to the z variable, and they enable us to say complex things inside the language. This is all in monadic predicate logic. It's straightforward to reproduce this in general predicate logic just by introducing some 3-place predicate. And here we've got 3 nested quantifiers, and in this case those 3 nested quantifiers are connecting up to a 3-place predicate, a, x, y, z. So this is what I mean by nested quantifiers, and now what we're going to look at is the way in which the ordering of this start of the sentence, regardless of what happens in the right-hand side, so without sort of messing around with the ordering in here necessarily, what happens when we start messing around with the ordering here. So for instance, if I take this same sentence and write it for all y, for all x, for all z, a, x, y, z, am I saying the same thing? Has moving the quantifier, that x quantifier, to the 2nd place and moving that y quantifier to the 1st place, has that actually changed the meaning of the sentence? And it's interesting because there are some cases where moving the quantifiers around like that makes no difference to the meaning of the sentence, and there are other cases where moving the order of the quantifiers really does make a difference. As a general rule of thumb, as we'll see, when all the quantifiers agree, you can mess around with your ordering as much as you want. So if they're all universals or they're all existentials, it's not really going to make a difference what order they are in before the predicate sentence that they connect to. When you've got a mixture, however, of universals and existentials, then the meaning of the sentence really does get altered by the ordering in which you have the universals and the existentials inside the start of the sentence. So we're going to have a look at exactly what those differences in meaning might be and how it is that we might think about them in a precise way. Okay, let's take a particular property. We're going to take a particular 2-place relation, and we're going to use that to think through our understanding of each of these quantifiers. So the 2-place relation that we're looking at is the loves relation. So this relation just says that x loves y. And so what we're now going to do is we're going to take all of our different quantifiers, universals and existentials and so on. And we're going to look at the different combinations you can have for the ordering of the quantifiers in front of this sentence in order to see what difference it makes, if any, to the meaning of the sentence. Let's start with the easy cases. When your quantifiers agree, when they are the same quantifier, whether they're universal quantifiers or existential quantifiers, the meaning of the sentence doesn't change. So if we have a look at this, we've got for all x, for all y, Lx, y. And now if I just swap the y and the x without making any other change to the sentence, so all I've done is move the universal with the x there and the universal with the y there. I've just swapped those places. If I make that change, I haven't changed the meaning of the sentence. This top sentence says everything loves everything, and this bottom sentence also says everything loves everything. So we've got something that is saying the same basic idea. It's not completely the same. There is a slight difference between the way that we might translate out these sentences. So this top sentence is really saying everything loves everything, and this bottom sentence is really saying everything is loved by everything. So for all things, for y, for all x, the second thing you pick loves the first thing that you pick. Sorry, for all y and for all x, the second thing that you pick, the second thing you pick loves the first thing you pick. That was right. So there's sort of slight difference in the way that you might read these back into English, but in terms of what they say logically speaking, in terms of the implications they have, if we were to try and understand the truth of these sentences by building models under which things are loving each other, the models would be exactly the same. So one way to think about what's going on here, which I find quite useful, is to think back to our picking things out of a bag, that sort of bag metaphor, and we're going to divide up our pick. So here we've got our first pick, and here we've got our second pick. Okay? So here's first and here's the second pick, and our two sentences are for all x, for all y, Lxy, and for all y, for all x, Lxy. Okay, now let's just suppose for simplicity we've got a very simple universe, and this isn't two distinct bags, this is the same bag for the first pick and the same bag for the second pick, and let's just suppose that we've got just three things inside our bag. So there are just three things to pick from. Now, if we look at this first sentence, what it's saying is that no matter what we pick the first time, that thing is going to, and no matter what we pick the second time, that first thing is going to love the second thing. So here's our first pick. What that means is that that first pick is going to love that thing. If we pick this thing the first time, then no matter which of these things that we pick the second time, this first thing is going to love those things. Similarly, if we pick this second thing the first time, then no matter what we pick the second time, that first thing is going to love those second things. And similarly, if we pick this bottom thing the first time, then that thing is going to love these things that we picked out the second time as well. So no matter what we pick here, it's going to stand in this loving relation to everything we pick over here. And that's what that first sentence says. But the second sentence is going to, if I were to draw a picture of the second sentence in this case, then it's going to look exactly the same. So this says for all y, for all x, Lxy. So no matter what I pick the first time, and no matter what I pick the second time, the thing that I picked the second time loves the thing that I picked the first time. So if I were to do that, then I would have this sort of loving relation go back this way. But the key thing here is that I drew the same number of lines connecting these things. So the sort of orientation of the arrow is different, and that's really the difference between moving the ordering of the quantifiers, is that I start sending the relation in the other direction. But because it's the same three objects over and over again that I'm picking, what I'm really saying in both cases, because all the arrows connect, everything is connected to something to each of the other things by an arrow. What I'm really saying is that everything loves everything, including itself, right? So you're drawing the same picture twice. You've just got the sort of orientation of the arrows working in different ways, but you're drawing the same number of lines. And it's really the number of lines coming from your first to your second pick or your second pick to your first pick that's going to be important in what follows. Core idea here, though, is that these two sentences are logically saying the same thing. If I'm drawing a picture of it, I'm drawing the same number of lines in the same configuration, and that's what's telling me that I've got the same thing going on between these two sentences. The same basic thing applies to the existentially quantified sentences. So when I've got these double existential quantifiers here, then I'm really saying pretty much the same thing in both cases. Again, we're going to get some interesting differences with the orientation of the arrows when I draw a picture of this, but basically the propositions are going to tell us the same things, logically speaking. So again, let's draw up our two bags. Here we've got EX, EY, LXY, and EY, EX, LXY. So again, I've just swapped the existential X into that second place and swapped the existential Y into the first place. Here's my first pick, here's my second pick. Same bag in both cases, three things in the bag only. In the first sentence, we're saying there is something I can pick the first time, and there is something I can pick the second time, such that the first thing loves the second thing, loves the second thing. So what that's going to look like is I'm going to have it be the case that something in that bag loves something. In this case, I've got it that it's loving itself. It's the sort of the loving relation is coming back, but you could have that something love any of the things that are in the bag. Right, that's what the first thing says. What I picked the first time loves something that I picked the second time, and in this case I picked the same thing twice. But I could equally draw a slightly different situation. I've got the same bags. So the first time around, I drew something coming from the first pick to the second pick, and I said that something loves something in the bag. The second sentence says something, for something I picked the first time, and for something I picked the second time, oops, I've reversed the variables here, sorry, that was an accident. For something that I picked the first time and something I picked the second time, the thing I picked the second time loves the first thing. So that means that I'm going to have an arrow coming back this way, and this is where the loving relation is going to lie. So that's the second sentence. Remember, the first sentence was like this. But you can see that essentially the same thing is happening in both cases. In the first case, we've got one thing loving itself, because this is the first pick and this is the second pick, and I'm picking out the same thing twice, and it's standing in that loving relation to itself. And in the second case, I've got the same thing I've got the same thing standing in that loving relation to itself in both cases as well. So in both cases, I've got something loves something else, and where the something else turns out to be exactly the same thing. Equally, I could have it the case that something loves something distinct if I were to draw the arrows in a slightly different way. All that really matters is that in both cases, we've got one arrow coming from one dot to the other dot. And that's all that sentence is really saying. It's saying there is something that stands in this relation to something else, or indeed to the same thing. We don't yet have a way of actually saying something else. We'll get to that later on when we deal with identity. The basic idea, though, is that we've got this relation standing between something and then that we picked the first time and then something that we picked the second time, whether it's the same thing or distinct things. It's just one thing standing in that relation to something else. And that's fairly intuitive, because what we're saying here is there is something that loves something, and here we're saying there is something that's loved by something. Both of those imply the same thing, namely that there's a love and there's a lover, and they stand in that relation. And so the two sentences are really saying the same kind of thing. Okay, so these two cases, the case of the universal quantifier and the case of the existential quantifier, those two cases really agree when no matter how you have the ordering of the quantifiers. You can sort of see that there's a slight difference to what they're saying in that the arrows are going from in one direction to the other, but the upshot, the sort of logical upshot, which is that you've got a love and you've got a lover, And in the existential case, you've got just one of those things, a love and a lover, and they're just connecting to each other. And in the universal case, everything is a love and everything is a lover, and they're all standing in that relation to themselves and to each other. A very exciting world indeed to live in. In both cases, you're saying exactly the same thing. You're not, in the case of ordering the existentials, in the case of ordering the universals, the ordering doesn't make a difference. The cases that we're going to look at are going to be more difficult in the sense that they don't have that same property. So if I start altering the ordering of the next cases that we look at, then we do get distinct alterations to the meanings of the sentence. And what happens is when we start using the existential and the universal quantifier in combination with each other, rather than having everything existential or everything universal, then we end up saying something quite different depending on the ordering that we have for the universal and the existential quantifier in question. So our first case that we're going to look at is for all x, there's some y such that Lx, y. So that's our first sentence. So this first sentence, what we're going to do is we're going to draw a picture of this. Again, we get our two picks, so we've got our two bags that we're going to draw up. And we're just going to put three things inside the bag. Remember, it's the same bag twice over. It's just that these are distinct picks from the same bag. And now what we're going to try and work out what this sentence says. What it says is that for everything I pick the first time, in other words, no matter what I pick the first time, there's something that I can pick the second time such that the first thing loves that second thing. In other words, everything loves something is what this sentence says. So everything that I pick the first time loves something that I pick the second time. So in order to represent this, what we're going to have to do is we're going to have an arrow coming out of each of the things that we pick the first time into some or other of the things that we pick the second time. So here we've got all of the things on the left, which is corresponding to the universal quantifier, and then all of the things, then something on the right, which is corresponding to the existential quantifier, and we've got this loving relation connecting them. Okay? So this is what that sentence says, everything loves something. And now what we're going to do is we're going to think about reversing the order of these quantifiers. So what happens when instead of saying for all x there's some y, lxy, I keep the lxy fixed and I just reverse the universal and the existential quantifiers. So what if I take this sentence and I turn it into this sentence? I turn it into there's some y such that for all x, lxy. So here now what I'm saying is I'm saying that there's something I can pick the first time that stands in the loving relation to, there's something that I can pick the first time such that for everything I pick the second time, everything that I pick the second time stands in the loving relation to that one thing that I picked the first time. There is something that is loved by everything. So what that means is that if I'm over here, I've got my first pick, I'm over here with my second pick, there's got to be something here that everything over here loves. There is something such that there is something I can pick the first time, such that for all of the things I can pick the second time, all of those things love that first thing. Everything, there is something that is loved by everything. So that loving relation coming back from that right-hand side. So you can see that simply by altering the order of those quantifiers, by making this existential and this universal quantifier in different places, I've actually managed to completely change the meaning of the sentence. It went from just having each of these things loving something over here to one thing over here being loved by everything, which is a completely different situation, a completely different state of affairs. So this is the first case where we really see this ordering of the quantifiers make a big difference to the meaning of the sentence. Okay, so that's just, on the slides, that corresponds to, let me see, 5 and 8. So what I'm now going to look at is 6 and 7, which are slightly different cases, but they do a similar kind of thing. So let's go to number 6. So 6 looks like this. Okay, so this is a slightly different sentence. So the previous two sentences we had, different orderings for our quantifiers, but we also had different variables in their places. So the last case we were looking at was this case: for all x there's some y such that lxy, versus there's some y such that for all x lxy. And what we've now done is we've moved from this sort of case to a situation where, in addition to reversing the quantifiers, like we're changing the ordering of the quantifiers, we've also changed which variables lie within the scope of which quantifiers. So over here we held that fixed. We said that the x is always within the scope of the universal quantifier and the y is always in the scope of the existential quantifier, and we've just switched which quantifier is in which place. Now what we've done is we've actually reversed the order of the quantifiers and we've reversed the variables. So we've now said that the universal corresponds to the y variable and the existential corresponds to the x variable. Okay, so what we're going to do is we're going to have a look at what difference that makes. So this is a sort of second kind of change to the ordering that you can make. The first kind of change to the ordering is to just reverse the quantifiers without changing the variables that appear inside the scope of those quantifiers. This second kind of ordering is reverse the order of the quantifiers and change the variables that lie within their scope. So now what we're going to do is we're going to see what difference this makes to the meaning of the sentence. Again, we've got our two bags. Here's our first pick. Here's our second pick. Now our first pick corresponds to the existential quantifier and our second pick corresponds to the universal quantifier. We've got three objects in these two cases. Again, it's the same bag twice over because we've got two picks. Now what we're saying is that there is something you can pick the first time such that no matter what you pick the second time, that first thing stands in this loving relation to whatever you picked over there in the second case. So what this means is that there's something here that loves everything. There is something such that no matter what you pick, that thing stands in the loving relation to those other things, right? So whereas the previous one we had everything being we had something being loved by everything, by reversing the variables and reversing the quantifiers, we then end up reversing that entire relationship. We end up with it being the case that something loves everything, which is another combination again. So the first combination we had was that everything loves something, so there's just sort of one line going from each of these three dots. Then the second case we had was that something is loved by everything, and then in this third case we've got that something loves everything. So again, we've changed the meaning of the sentence quite substantially, and all we've done to change the meaning of the sentence is just mess around with the ordering of the quantifiers and the variables. All right, the last case that we're going to consider is like this case, except what we now do is we reverse the existential and the universal. Okay, so now what we've got is, for all y, there's some x such that lxy. What this sentence says is that no matter what I pick the first time, there is something I can pick the second time such that that second thing loves one of the first things, right? So in other words, for everything, there is something that loves that thing. So if I were to draw a picture of this, here's what I'd end up with. So here's my first pick. No matter what I pick the first time, there's something over here that I can pick the second time that loves the thing that I picked the first time. So here we've got a slightly different combination again. In this case, we've got the loving relation coming from the second pick back to the first pick. And in the actual sentence, what we're saying is that everything is loved by something. So we've got four different ways of ordering these quantifiers, whether we change the ordering of the quantifiers or change the ordering of the variables, and we end up with four different combinations or four different patterns that represent slightly different relationships. So let's just summarize all of those relationships by drawing up all of the four different diagrams that we had, and then once we've got those four diagrams, we'll have a look at the relationships between them. So here are the four diagrams that we had. Okay, and now we can start to write out what each of these corresponded to. So this first one up here was for all x, there is some y such that Lxy. The second one over here was there's some y such that for all x, Lxy. This one down here was there's some x such that for all y, Lxy. And this one here is for all y, there's some x such that Lxy. So those are our 4 different combinations, and you can see the 4 different diagrams that correspond to each of those combinations. And those 4 different diagrams are representing different situations, different states of affair, different ways of thinking about the world. So this first one is that everyone loves something. This second one is that something is loved by everything. This third one is that something loves everything. And this fourth one is that everything is loved by something. And now you can start to see that there are clear relationships between these 4 pictures. In particular, across the diagonals, we end up with if we were to take the diagrams and put them against a mirror, we would see we'd produce the second diagram. So if you take for all x some y Lxy and you reverse the variables without reversing the quantifiers, then you end up just sending the relation back the other way, but in exactly the same kind of way. So you just end up mirroring the relation. And similarly over here, if we reverse the variables without reversing the quantifiers, then you also end up reversing the relation back on itself, but keeping the structure of the relation intact. So, basic summary of what's going on here, overall general picture, is that when you change the order of the quantifiers, you change the structure in a really deep way. So if I change the order of the quantifiers, I end up moving from this kind of structure to this kind of structure, and those are quite different. If I change the order of the variables without changing the order of the quantifiers, then I don't end up changing the structure in a really deep way. Rather, what I do is I just end up inverting the relation that I'm interested in. I end up bringing the relation back on itself. And so the sort of difference that goes across the horizontals here is much greater than the difference across the diagonals. Similarly, the difference on the verticals is also much greater than the difference across the diagonals. You've got sort of deep structural differences between these and between these, but very sort of symmetries or mirror reversed relationships going in those directions. Now, of course, this is just for 2 quantifiers. If I add in a third quantifier, then I'm going to end up with a greater space of possible variations for the quantifiers that I'm dealing with. If I add a third quantifier, then I end up with a third line of dots, and then I end up with combinatorially more options, more ways to send the relations, and more types of possible structure that could underpin the particular quantifiers that I'm actually drawing out and the structure of the sentences that I'm interested in. More generally, as you sort of dial up the number of quantifiers, you also dial up the number of structural possibilities or structures of this kind that you can actually represent. And that's really that's one of the sort of powerful features of general predicate logic, is that by adding more quantifiers and more complexity, we get a greater ability to represent a more varied range of structures in the world, right? So we can represent these 4 structures just using these quantifiers and messing around with the variables, add more quantifiers, add more variables, and we can map pretty much any kind of structure that you might be interested in that has this kind of relationship between a universal and an existential. When you're doing translations, when you're trying to translate out English into general predicate logic, you have to be really careful to keep track of the ordering of the quantifiers, because if you get the quantifier ordering wrong, even if you get the sort of variables correct in the predicate that follows the quantifier, if you get the ordering of the quantifiers wrong, you might well end up representing a different kind of structure to the kind of structure that you're trying to represent. For instance, suppose you want to say that everyone loves at least one person, but you end up getting the order of the quantifiers wrong and writing this, you end up saying there's someone that loves everyone. And that's quite a different thing to what you're trying to say. So you've got to be very, very careful about how you order these quantifiers when you're actually producing translations of English sentences. And one of the hardest things, I think, to do with general predicate logic is keep track of this phenomenon, particularly when you dial up the complexity here and you add in more quantifiers, more variables, more structural possibilities. There's more to keep track of. So just make sure sure that you keep a sense of what's going on. If in doubt, try drawing out these kinds of diagrams. As I said, you can draw these kinds of diagrams even when you've got 3 different quantifiers. So have a look at this. For all x, there's some y such that for all z. And I want to suppose I've got a 3-place relation, and this relation we'll suppose is the relation x is between y and z, right? So it's this kind of relation. If I want to draw it, like just get a sense of what's going on with this, I can draw exactly the same kind of diagram and map the kind of structure that this relation requires. So what is it saying? It's saying I got my 3 picks. It's saying that for everything I pick the first time, there's something I can pick the second time, such that for everything I can pick the third time, the thing that no matter what I pick the first time, there's something I pick the second time, and for everything I pick the third time, such that this relationship will hold. So what's that going to look like? Well, let's just take it in steps. Ignore the thing beyond the existential for a moment. We've got for all x, some y. So remember, I know how to do that. I know how to represent for all x, some y. I know that for all x, there's got to be some y that it gets sent to. Now, I ignore that first bit and I just look at there's some y for all z. I know what that looks like. I need to take one of these and send it to everything over the right here. So if I do that, then what I've managed to do is I've managed to map the structure. So those 4 basic structures that I identified for you with the 4 different combinations of quantifiers can actually be used to model the structural relationships between these quantifiers of arbitrary complexity. Because you can always just sort of break it up into pairs. And by breaking it up into pairs, you can just take pairs of those structures and squash them together in order to get a sense of what's going on. All right, so if I had 4 quantifiers here, I'd have 4 sets of dots, but I would just take it in pairs. I'd go first and second, second and third, third and fourth, and I'd use that to build the structural relationships that I was trying to model and to keep my sense of the ordering of the quantifiers. And once I've got this picture going, I can then mess around with the ordering of the quantifiers in order to say slightly different things. So for instance, I could swap the for all z and some y, and now what I'm saying is that for all x and for all z, there's some y. So no matter what I pick out here, and no matter what I pick out here, and for something that I pick out here, this relationship is going to hold. And remember if I just focus on the for all x, for all z, remember what that relationship looks like. That relationship involves everything on the x side being sent to something over there with the z. So I'm going to have, instead of so now the z is my second pick, remember? So if I just look at the x and the z, I know that what I'm going to have is everything over here being sent to everything on this side, for all x, for all z. And then when for all z, for all y, I know that for all z, for some y, I'm sending each of these things to one of those things over there. So I'm going to end up with something like this kind of structure. And now I can represent this complex 3-place relationship by looking at any of these arrows from the start to the finish. So the sort of L relationship is across all 3 of them, and any way of following these arrows through from the left to the right is going to give me a way that this sentence can be, structurally speaking. So all I did here was just take those 2 of those basic structures that we had before and squash them together, and then move the order of the quantifiers, take different structures, and then squash those together. As long as you've got an understanding of what those basic structures are for the different ordering relations of the quantifiers, then you can produce one of these diagrams in order to understand the relationships between the quantifiers and what they're actually saying about the thing, the sentence here that they're quantifying over and that they're binding. Okay, so what I'll do now is I'll give you some quick examples. I'll work through some of these cases. I'll do some translations for you. And then from there, we're going to add one final moving part to general predicate logic to finish off the syntax. So here's a claim. For each thing, there is something that it is bigger than. So for each thing, there exists something that it is bigger than. So what I'm going to need is a 2-place predicate. X is bigger than y. And if I want to say for each thing there is something that it is bigger than, what I'm going to say is that for all x, there exists some y such that x is bigger than y. And remember that the sort of structure that I'd be drawing here, for all x, there's something that it is bigger than, would be this kind of structure. For each of the things I can pick the first time, there's something I can pick the second time such that the thing I picked the first time is bigger than this thing I picked the second time. Next claim, there is something that each thing is bigger than. There is something that each thing is bigger than. So there exists something such that for all y, y is bigger than x. So there exists something such that everything is bigger than that thing. So if I were to draw a picture of this, I'd end up with something like this picture. There exists something such that everything is bigger than that thing, where the bigger than relationship here is going from right to left. Okay, next example. Everything is bigger than something that is bigger than itself. So how do we say that something is bigger than itself? Let's start there because that's the new bit, and then we can look at the rest of it, namely everything is bigger than something. So how do you say that something is bigger than itself? Well, the easiest way to do that is to say something like this. First of all, we're going to have a quantifier for this thing, and we're trying to talk about the things that are bigger than themselves. What we're really saying is that everything is bigger than something that is bigger than itself. So for everything that is bigger than itself, there's something. Everything is bigger than something that is bigger than itself. So what we've got to do is we've got to work out how to conditionalize on the things that are bigger than themselves and then talk about how that connects back to this everything is bigger than something part. So if we want to say that something is bigger than itself, the easiest way to do that is to that gets us, there is something that's bigger than itself first. It gets us something like that last part. Now we want everything is bigger than something. So we know how to do that. For all x, there exists some y such that x is bigger than y. And now what we want to do is we want to connect these two ideas. We want to connect the fact for all x there's some y that x is bigger than, and we want to stipulate that that y is bigger than itself. So what we do is we connect these two ideas into something like the following proposition. For all x, there's some y such that x is bigger than y and y is bigger than itself. So that gets us everything is bigger than something that is bigger than itself. So for all x, for all the things we can pick the first time, there is something we can pick the second time such that the thing we picked the first time is bigger than the second thing and the second thing is bigger than itself. Now note that we can say this. We can say that something is bigger than itself, even though that might not make much sense to us. It can be hard to make logical sense of the idea that something is bigger than itself because that seems like a contradiction or it seems like something that's incoherent. Later on, we'll see how we can make that precise. At the moment, we don't really have the resources in order to say enough about the bigger than relation that's going to force this to be incoherent. So far, for everything we've said, we haven't been able to restrict that worrying case where something is bigger than itself. In order to do that, we'll need to add further moving parts of the relation. We can have a look at that as we go. All right, something is bigger than everything that is not bigger than itself. So let's do the something is bigger than everything. So there exists something such that for all y, x is bigger than y. So that gets us something is bigger than everything. And now we want to say something is bigger than everything that is not bigger than itself. So something is bigger, there exists something such that for all y, if it's the case, hang on, I'm going to need. There exists something such that for all y, if x is bigger than y, so if something's bigger than that thing, then y, it's not the case that y is bigger than itself. So something is bigger than everything that is not bigger than itself. So there exists a thing such that for all y, x is bigger than that thing, right? And if that's the case, if there is such a thing, then those things that it's bigger than are not bigger than themselves. Okay, so there is something such that for all y, if bxy, then it's not the case that byy. All right, next. Everything is bigger than everything unless something is bigger than nothing. So everything is bigger than everything is easy for all x, for all y, bxy. That's the easy part. And remember, with working with unless, the easiest way to deal with unless is to just translate it out as a disjunction. And now we want to say something is bigger than nothing. So to say that, we need to say that there is something that isn't bigger than anything. So there exists an x such that for all y, it's not the case that x is bigger than y. All right, so there is something such that for all y, it's not the case that x is bigger than it. So x is bigger than, it's not the case that x is bigger than anything. Something is bigger than nothing. Okay? And if we want the conditional form here, we can just translate out that disjunction into one of the other conditionals by either negating the left-hand side and using that as the left-hand side of our conditional, or negating the right-hand side and using that as the left-hand side of our conditional. Okay, so that's GPL syntax and some examples of how to apply it to some tricky cases. These are sort of deliberately tricky cases. And what you've got to do in each case is try and work out the ordering of the quantifiers in order to get the right kind of relationship out. It's possible to do this in your head in the way that I was doing it, to just sort of think through the case, work out which order that has to be in and how it's going to have to work. If in doubt, though, you can draw some of those pictures in order to draw out the case and in order to understand which order the quantifiers need to go in. And that, by drawing those pictures, you can sort of see very visually how it is that, you know, the relation of bigger than is going from one side to the other, or the other side to the first side, and then using that information, try and translate out the ordering of the quantifiers. But this is hard. This is probably the hardest thing you'll have to do with respect to translation, is try and work out how to order these quantifiers. And really the only way to get proficient at it is to do a lot of different cases. And you can do these cases just by making something up. You can make up everything is bigger than something, those sorts of cases, give them to each other to test, practice with each other, look over each other's translations and try and work out what the right kind of translation ought to be. All right. What I'm going to do now is just finish off general predicate logic by looking at one last kind of argument that we can't actually handle using the syntax that we've got so far, and that we're going to need to modify our language in order to be able to accommodate. So consider this kind of argument. First premise, the morning star rises. Second premise, the morning star is the same thing as the evening star, therefore the evening star rises. So what we've got in our language so far are predicates for monadic properties, you know, property of being red, things like that. We've got relations that specify a connection between two or more things, and then quantifiers that specify how those relations work. But what we don't have is any way to say that this thing is the same as this other thing. And so in this argument, that's exactly what we're using. We're using this claim that the morning star is the same thing as the evening star. And as you can see, this looks like another valid argument. This looks like the kind of thing that our language of logic should be able to handle. But because we don't have any way to talk about X being the same thing as Y, or talking about the morning star being the same thing as the evening star, as in this case, we don't have the capacity to be able to translate out this kind of argument either. So what we do now is we add in an extra moving part, and that extra moving part is the concept of identity. The idea that one thing is equivalent to or is the same thing as another thing. Now we're going to use the identity sign, so we're going to use the equal sign for this. It shouldn't be confused with the equal sign necessarily in mathematics. It's not exactly the same thing. When we use this equal sign, what we're saying when we say something like A equals B is that the object that A picks out in the world is the same object that B picks out. So the way that we tend to think of this is in terms of co-reference. So the reference of a term, or the thing that the term refers to, is the particular object in the world that, say, a name refers to. So my name, Sam, refers to a particular object, me. Your name refers to a particular object, you. But what we can have are multiple names that refer to the same thing. So if the morning star and the evening star refers to the same object, and which in fact is the case, they both refer to the planet Venus, then the morning star and the evening star are co-referring terms, and we can represent that using this item in our language. We can say that A, the name for the morning star, is the same thing as, it picks out the same thing as the name B for the evening star. So we're going to use this to be able to say things like that, to be able to identify things inside our language, to be able to say this is the same thing as that thing. And once we've got the identity sign inside the language, we're going to be able to say some very interesting things, syntactically speaking. Okay, so if we include this little syntactic item into our language, then we can say things like this. We can say that the morning star is the same thing as the evening star, which gives us the capacity to translate out this argument that we had back here, namely the morning star rises, the morning star is the same thing as the evening star, so the evening star rises. So what we do to translate this out is we say that A corresponds to the morning star, B corresponds to the evening star, and then the predicate R is the property of rising. And so now we can just translate this out as follows. The morning star rises. The morning star is the same thing as the evening star. Therefore, the evening star rises. So RA, A equals B, therefore RB. Again, later on, we'll be able to prove that this is a valid argument, but as yet, we don't have the capacity to do that. All we've got is a syntactic construction for representing identity or equivalence. Later on, we'll be able to include that in our proof theory and use that inside the tree system to actually come up with proofs of arguments like this. But for now, all I want really is the ability to just translate out the claim that we're interested in so that we can at least translate the arguments that seem to us to be valid into the language that we're working with. All right, now here's the interesting thing about the identity relation. The identity relation the identity symbol is really a two-place relation. So what we've been looking at so far are things like TXY, which is the relation of being taller than, and that's a relation between X and Y, between whatever it is that stands in the first place, whatever it stands in the second place. And identity, this thing, is really working in a very similar way. It's got two slots, one slot on either side, so it's a kind of two-place relation. And you can put anything you want in there. So you can put a variable and a name. You can put two names, the same name twice. You can put two variables in there. You can put the same variable. So it really acts in exactly the same way as the two-place predicates that we already have in the language, at least syntactically speaking. It's just that notationally, it looks a little bit different. Now, later on, we'll see that there is a big semantic difference between things like the TXY, which is the taller than relation, and this identity predicate, which is also representing a relation between two things. But for now, syntactically, we can actually see that there's a deep similarity between the two. Because later on, semantically, we're going to pull apart identity from other features of the language, like these other two-place relations. What we're going to do now is we're going to mark that future difference in semantics syntactically, and that's why we use this identity sign. So although, technically speaking, the identity is just a two-place predicate, and you could just represent it like this. X is identical to Y. You could just represent it in the same way that we represent taller than or bigger than or any of the other relations. What we actually do is introduce this new sign, this identity sign, to mark the difference between this particular two-place relation and the other two-place relations that are inside the language. So what that means is that there's sort of good news and bad news. The good news is that the identity predicate is already kind of contained within the syntactic definitions for general predicate logic that I gave you. The bad news is that it's kind of hard to see that identity is in there because identity, when it's just being treated as a normal two-place predicate, just gets captured by that first clause in our definition of the syntax, and so you don't get really sort of see it marked out specifically in the statement of the syntax. So what we can do, if we really want to, is alter the syntax of the language in order to include something like identity. And so that's what I've got on this slide, is that we actually add an extra clause that determines how it is that we use the identity relation inside the language. And the syntactic clause is very simple. All it says is that you can put whatever you want on the two sides of the identity symbol, and that's syntactically acceptable, so long as the things that you put in are either names or variables. So as long as you put names or variables on the two sides, and as long as both sides are filled, you've got something on both sides, then you've got something that's syntactically well-formed inside the language. All right, the last thing that we need for our language is a way to talk about non-identity or distinctness. So this tells us that A and B are the same thing. It allows us to talk about, the morning star and the evening star being the same thing. But sometimes we want to talk about two things being distinct. So we want to say that Mars is not the same planet as Venus. Now, the way that we represent this is to take this identity sign and to put a slash through it. So we're saying A is not identical to B. Technically speaking, we could do this instead. We could take this two-place identity predicate, which this is, we could represent it with an I, and then we could just put a negation out the front in exactly the same way that we put a negation out the front of any two-place or three-place or four-place predicate inside general predicate logic. So we can treat it syntactically just like the other predicates. But again, because the semantics for this thing is going to be treated differently to the semantics for things like taller than, we're going to give it a slightly different syntactic marker so that we can keep aware of that semantic difference later on. So what we do is, instead of just using the negated I predicate or a negated two-place predicate, we introduce this slashed equality. And as with the identity predicate, we can introduce this syntactically into the language using an extra clause if we want to. If we want to draw out explicitly that these two syntactic items are sort of added into the language in addition to the basic predicates that we've got, then we can add these clauses. For my purposes though, I'm just going to focus on this general syntactic construction, which does subsume a two-place predicate which corresponds to identity, because really, syntactically speaking, that identity predicate is not doing anything different to any of the other two-place predicates that we have in the language. All of the work is going to be in the semantics, and so that's where we're going to pay the closest attention to this identity predicate. All right, now once you've got identity in the language, you're actually able to say some pretty interesting things. So have a look at this sentence in English. So here's a claim: there are at least 3 dogs. It seems like a fairly plausible claim about the world. If we want to translate this claim out, we can now translate it out using identity. We actually couldn't translate this out before when we didn't have identity kicking around in the language. So here's how we do it. We say there exists an X, there exists a Y, and there exists a Z, and they're all dogs. So dx and dy and dz. So that gets us there are at least 3 dogs, in the sense that if we had a bag, we get to pick 3 times. You could pick 3 things and they'd be dogs. But as I said before, when we're picking from that bag, we put the things back in, so it's compatible with picking from that bag that we pick the same thing 3 times. So this here doesn't yet say that there are at least 3 dogs. All this says is that I can pick 3 times and I can get 3 things that are dogs. What I need is some way to say that my 3 picks are going to be distinct. They're going to pick 3 distinct dogs out of the bag. So to do that, I chain a series of non-identity or distinctness statements to this particular claim. So I say things like X is not identical to Y, and Y is not identical to Z, and X is not identical to Z. So if I add these 3 conjunctions to it, what I'm saying is there are at least 3 dogs, and the first dog is distinct to the second dog, and the second dog is distinct to the third dog, and the first dog is distinct to the third dog. So if you imagine picking things out of a bag again, I get to pick 3 times, and what this forces me to do is pick 3 things where I end up with 1 dog over here, I end up with a distinct dog over here, and then I end up with another tiny little dog over here, and they're all different dogs. Right? So that using that identity, that slashed identity symbol, allows me to differentiate between the things that I pick out of the bag. Okay, so that's kind of cool. We get to be able to say that there are at least 3 dogs, but we can actually do something even more complex than that. So we can also say that there are, if we want, we can say that there are exactly 3 dogs. So how do we say that? Well, what we do is we start with there are at least 3. Start again. Okay, start it with at least 3. And to do that, we add in that chain of non-identities. Right, that ensures that the 3 things that we're talking about are distinct. So that gets us there are at least 3 dogs. And so what we're saying is that if we pick from the bag 3 times, then and we pick 3 dogs, then we're going to be able to, it's possible to pick 3 distinct dogs. Now what we want to do is we want to say, and for anything else that we pick from the bag that's a dog, it's the same as one of those 3 dogs that we picked, which is to say that we can pick 3 distinct dogs, but if we were to keep picking from that bag forever, we wouldn't be able to pick a 4th dog. We wouldn't be able to pick a unique dog from the bag. So the way that we do that is we actually add in a universal quantifier over here that quantifies over the entire statement, and it says, so we sort of allow for this big conjunction of claims about dogs and the distinctness of dogs, and then we add to that, and for all things that are W, if W is a dog, then it has to be either, it has to be either the first dog or the second dog or the third dog. Right? So here's the full-blown translation. Here we've got there are at least 3 dogs. That's that whole chunk there, which is saying that you've got 3 things that are dogs and they're all distinct. And then you say, and for anything else, if it's a dog, then it's one of these things, one of these 3 things that we pulled out. And what that ensures is that you can pick at least 3, but you can't pick any more. So that's going to force it to be the case that there is exactly 3 dogs in the bag. So not only do we have the capacity using identities to say that there are at least 3 things, we can also say that there is exactly 3 things, or there's exactly any number of things. If we want to say that there's exactly 1 dog, then we can do that just as easily. We say, first of all, we say, what is it doing? We say there exists a dog, and for all things, if they're dogs, then they're identical to that first dog that we picked. So this gets us that there's at least 1 dog, and then this tells us that no matter how many times we try and pick another dog, we just end up picking that 1 dog over and over and over again, and so this gets us exactly 1. And if we look at that structure, if we look at that sort of translational structure, that broad structure gets retained no matter how many things we're trying to say there are exactly that many of, right? So if we want to say that there's exactly 2 things, what we do is we add another existential. We say there are at least 2 dogs, and then we add the distinctness claim, X is distinct from Y. And then we say that for all of those dogs, either they're distinct to the X dog or they're distinct to the Y dog. If you want to say that there's 3 things, you say there is an X, there is a Y, there is a Z, and they're all distinct and they're all dogs, and for any W that you pick out, it's one of those, it's either X or Y or Z. If you want to say that there's exactly 4 dogs, you say there's an X, there's a Y, there's a Z, there's a W, and for any T that we can pick out, it's the same as one of those first things that we picked out, and so on. The basic structure doesn't change as you dial up the complexity of the claim that you're actually trying to translate out. Okay, so we can say there's at least, we can say that there's exactly. The third interesting thing that we can say with the language is that there is at most 3 dogs. So if we want to say, actually I'm going to simplify this a little bit. So I'm going to say there's at least, at most 2 dogs. And the way that we say this is slightly different. What we're trying to say, because when we say that there's at most 2 dogs, we need to leave it open that there's actually no dogs at all, because it says there's at most 2, but there could be none. So we can't use any existentials, first of all, because as soon as you use an existential quantifier, it's going to establish that there's at least 1 dog. But we want to leave that open because we want to leave it open that there's no dogs. We just want to say that there's at most 2. So everything that we say here is going to have to be framed using universal quantifiers. And so here's the way that we say it. We say for all x, for all y, and for all z. So we get 3 picks. And let's suppose that we pick 3 dogs. All right, so for all x, for all y, for all z, if x is a dog and y is a dog and z is a dog, then what? Then either x is identical to y, or y is identical to z, or z is identical to x. All right? So we've got now a sequence of disjunctions that connects to that main conditional. So what we're saying is that for all x, for all y, for all z, if x is a dog and y is a dog and z is a dog, then either x is identical to y, or y is identical to z, or z is identical to x. So what is this actually saying? We'll come back to our bag. We get 3 picks from the bag, and let's suppose that we pick 3 times, and we get 3 dogs, right? That's what this first part is telling us. What it's then saying, so here we've got first pick, second pick, and third pick. What it's then saying is that either these 2 picks are the same dog, or these 2 picks are the same dog, or these 2 picks are the same dog. Which is to say that, yes, we can pick 3 dogs, but for any 3 picks that we make, where all of those picks are dogs, at least 2 of those dogs are the same dog. So we can pick 3 times, but you can only ever pick at most 2 dogs because you keep picking the same dog at least twice for the 3 picks that you make. So in other words, if you've got a big bag full of dogs, you get to pick 3 times. At best, you're going to end up picking 2 distinct dogs and then one of those 2 dogs a second time. And that's what this whole sentence here forces you to do. All right, so what that means, if we put this all together, we can say at most n, so we can say at most n objects. We can say at least n objects. And we can say exactly n objects. So we can say all 3 of those things using only the terms inside general predicate logic. And these are all called numerical quantifiers or numerical quantification. And it's numerical because we get to talk about the number of things that there are. And this is really, really useful because we often want to talk about there being at least so many things or at most so many things or exactly so many things. So it's really useful for being able to translate out arguments. But it's also really useful for that other thing that I was mentioning about logic, namely this goal of trying to capture everything inside mathematics using purely logical terms. Because once you've got the ability to express numerical concepts like this, you seem to have the ability to start to do things like talk about numbers, talk about the relationships between numbers, say how many numbers there are, and so on. And so it starts to look like you can rebuild chunks of mathematics using the basic resources that we have inside logic. As I said before, turns out you can't do this completely, you can't rebuild all of mathematics. But I think it's very interesting that you can at least get this far. You can start to express these fairly complex numerical concepts using only the resources available to you inside general predicate logic. All right, that finishes off the syntax for general predicate logic. What I'm going to be doing next time is taking you through the semantics. I'll tell you how to take the semantics of monadic predicate logic, the model theory, and expand it and complexify it in order to generalize it into the general logic case. Okay, good luck.